Hello, now we are seeing Theory of Computation subject Supplementary Examination Summer 2022 question papers answers. So, in first question, find DFA that accepts only the language of all strings with B as the second letter over the alphabet. Sigma is equal to A comma B. So in this question we have to construct a DFA that will be accepting only the language of the strings in which the second letter will be B and the input, that is sigma, is equal to A comma B. So the given data we can write like here. Given data is sigma is equal to A comma B, and now constructing the DFA. So this is the DFA, and in this DFA, starting with initial state, let's suppose we take capital letter A. This is our initial state, and the first input doesn't matter whether it comes A or B. So we write A comma B, and we take second state as capital B. We can take any alphabet, it doesn't matter, but here the thing matter is the second input, that is second letter over the alphabet B we have given in question. We will write as it is. If the state B gets input B, then we reach it to the final state, we name it as C. But here one condition remains, because in DFA, that is determines finite automata, every input condition needs to be checked for the DFA. So when this B state get A, we have to trace some transition. So we move it to the another new state, that is dead state, name as D. And for that dead state, whether it gets A or B, it will remain in dead state. And in final state, we don't bother about what we get A or B. So we draw a self loop so that whatever input gets, whether A or B, it will remain in C. So this is the right approach, but another way also is there, like this DFA. But comparing with this DFA and this DFA, the first DFA is right, because we need such DFA that is what we say efficient or with less number of state. But here the states is 1, 2, 3, 4, 5 states. But in first DFA there are only 1, 2, 3, 4 states. So first one is better option rather than this. This is also true, like if A gets input A, then it goes to B state, and if get B input, then go to C state. But the second symbol remains same, BB, so it goes to final state. But here one state increases, so it is not suggested. Next question. Construct a Mealy machine of the following Muri machine. So here we have given one Muri machine, and we have to construct a Mealy machine from this Muri machine. So this Muri machine's output is 0, 1, 2 to the respective states Q0, Q1 and Q2. So we will write the given data. Here the given data is equal to sigma, input is 0, 1 and del, that is output 0, 1, 2. And now we will draw the transition table of this Muri machine. So we will write first in column states, then the inputs 0, 1 and the output. So the initial state is Q0. So we will write all the states here, that is Q0, Q1, Q2. And when Q0 gets input 0, then it remains on the Q0 state. So we write as Q0 here. And when Q0 gets 1, it goes to Q1. So we write here Q1. And we know the output of Q0 is 0. Now the next state Q1. When Q1 gets input 0, it goes to Q2. So we written Q2 here. And when Q1 gets input 1, it goes to Q0. So we written here Q0. And the output of Q1 is 1. So we write here 1. And now the next state, that is Q2. When Q2 gets 0, it goes to Q1. So we write Q1 here. And when Q2 gets 1, it remains on Q2. So we write Q2 when Q2 gets 1. And output is 0, as here we can see. Now the above table is the transition table of Muri machine that we just saw now. Now let's see the transition table of Mealy machine. So let's construct the transition table of Mealy machine. So we just have to write the states as it is and the inputs 0 1. No need to write the column of output, because in mealy machine the output is associated to the input. It is related to input and states, but in Muri machine the output is associated to only state. So here no need this. And now let's see the transition table of Muri machine. Here we can see when Q0 gets input 0, it remains on Q0, and the Q0's output is 0. So we will write Q0 comma 0, that is its output in mealy machine's transition table. And when Q0 gets 1, it is on Q1. But here the output will be Q1's output, that is 1. Like here it is there, Q0 when gets 0, it remains on Q0, output 0. And when Q0 gets 1 input, it goes to Q1 and output 1. And the rest is also same like that as I told now. Therefore the mealy machine is this. So according to this transition table, we have to draw this mealy machine. Like if Q0 gets 0, then it remains on Q0 and output 0. So like starting state, initial state Q0 gets input 0, it remains on Q0, output 0. And when gets 1, it goes to Q1. So we will make this transition. When get 1, it goes to Q1 and output Q1 is 1. And like similar way we have to construct this mealy machine. Now let's see the another next one question, that is construct the DFA for the following NFA. Now this is one NFA diagram, and we have to construct the DFA for this. So for constructing the DFA for the NFA, we have to first of all construct the transition table of NFA. So the NFA is given in question. So according to it, we have to construct the transition table, like states column, inputs column, and here inputs are 0 and 1, and initial state is Q0, and when Q0 gets 0, it goes to Q4, and when Q0 gets 1, it goes to two states, Q1 and Q2. So we will write by separating comma, and like it is we have to write this. And when Q1 gets 0, it has no transition, so we write 5. And in this also some exceptional cases. Now let's construct the transition table of DFA from the NFA table. So first of all we have to write the first initial state as it is from NFA, like Q0, and when get 0, Q4, like here you can see. And here there are two states, Q1 comma Q2. So in DFA we have to combine these two states and form one new state, that is Q1 Q2. And now we have to construct this transition table of DFA according to what we get in this input new states. Like here Q1 Q2 and Q4 two states are there, so we only write these two states in this column. Like in states, now Q1 Q2 we get a new state, so we write here Q1 Q2. And when Q1 Q2 gets 0, here there is no Q1 Q2 state, so we have to combine this Q1 and Q2 and check this or combine these inputs also. Like when Q1 Q2 gets 0 input, then here the 5 so we will add new state, that is Q5. Sorry. And when it gets input 1, then there is 2. Like in Q1 if we get 1, it is Q0 transition, and when Q2 state gets 1 input, then the Q3 state is there. So we combine these two and form a new state, that is Q0 Q3. Like here see, as I say, new state, dead state Q5, not dead state but new state. And in get 1 there was Q0 comma Q3, but we combine this. Now here new state comes, this and this one, so we write this now here. We can write any one, but it is like if we write Q5 first, then we have to write this step there. But since this is some complex, we write first it. Now Q0 Q3 new state. Now see first table, Q0 Q3. Here combining input 0, Q4, Q0. So new state Q0, Q4, and here Q1, Q2 and union 5. So no union, only Q1, Q2. Like here is there Q0, Q4 and Q1, Q2. And same it as for Q0, Q4. We will get this, and now these are same state, so no new state comes. So we will write only these two states are remaining for that transition. So for Q4 state we will write here, like this is 5 this is dead state, like no dead state means no transition. So we will write the new state Q5 as a dead state we consider. So here we will write rather than writing 5, we will write this new state Q5. And for Q5 it also remains on Q5 when input 0 and 1 occurs. Now finally we are going to construct the DFA from this transition table of DFA. So this is the final output, like DFA, like see Q0 if get 0 it goes to Q4, Q0 get 0 goes to Q4, and when Q0 gets 1 it goes to Q1 Q2, again it's 1 it goes to Q1 Q2. Like from this transition table we have to construct this DFA. Now the next question 2a, explain Chomsky classification of grammars. So this you can find very easily on internet. This is a theory question. Like basically there are 4 types of Chomsky classification of grammars. First one is type 0, that is unrestricted grammar. Then type 1, that is context sensitive grammar. And then type 2, that is context free grammar. And at last but not the least, type 3, regular grammar. And this is full of theory. Like if you have tutorial, then you might see the answer in tutorial notebook also. Otherwise internet there are a lot of theory, so you can take reference or read anything which is easier to you for better understanding. And now the next question is, consider the grammar given as G is equal to S, A, B, P, S, where production P consists of here the production rule. So basically grammar first is, this is non-terminals, this is terminals, this is production rule, this is start symbol. And we have to find leftmost derivation, rightmost derivation, and the parse tree, that is derivation tree for the string AA, BB, AA. So first of all we write this given production rule in step by step. Like here it is combined, like S produces A, AS or A. Sorry, then we write it is separate. S produces A, AS 1, give production number 1. Then S produces single A, that is 2, and simplify the given production. Then leftmost derivation means starting the derivation from leftmost non-terminal. Here there are 2 non-terminals, capital letter A and capital letter S. So we will derive from leftmost non-terminal. We will first solve this capital A, then we will go to capital S. So we have to derive the string A, B, AA. So we will use this first production rule, then we will derive this first leftmost derivation, like A right as it is, A4 we will write SBA, it is as it is. So from where SBA got? From production number 3. And according to it we have to solve this, and then we will get this string. Like from further S we will calculate A, and then we will calculate AS, BA, then SS, then see this production. And same for the rightmost derivation. We have to take care that we have to write this symbol of derivation production. Then the derivation tree or parse tree or derivation tree. So from here A S A S, then A, and like we have to derive the tree according to the production rule. We can choose anyone, like anything, like leftmost derivation or rightmost derivation, because both are same. Now let's see the next question. Find a reduced grammar G to the grammar given below. This is the grammar, and we have to reduce this grammar G. So for this there are some rules, like if one is producing AB, then AB must be there here in production, and AB must produce some, at least any string of terminals, otherwise there is no use of AB. And if any CA is producing, for example I am telling, if CA is producing epsilon, then there is no need of CA here. So we have to eliminate these unnecessary symbols. That's it. So here, as we notice, there is variable B which is not deriving any. So we notice this B. This is as it is, BC and AB. There are no AB and BC. And if there are no, but if it is producing BC, C have one terminal. But what about B? It is again producing BC and AB. So as like AB also, A is producing a terminal A, but what about the B? So it is unnecessary symbol. So let's terminate this one. String of terminal, those it is useless symbol. For remaining B to get reduced form of grammar, should delete all the production for which B is appearing on the RHS of them. Clearly we can remove B producing BC and AB, because again B is there is in RHS which is not producing any string of terminal. Therefore it is like unit production type. But also S producing AB and C producing AB, that we can drop to set simplified grammar without useless symbol as. Now the reduced grammar is S producing CA, A producing A, and C producing B. Here A and C can be derived from start symbol, so no problem. So the next question is, convert the following CFG, that is context free grammar, to CNF, that is Chomsky normal form. This is grammar. Now what is Chomsky normal form? Chomsky normal form is that production some restrictions are there. Either S producing AB, that is only two non-terminals, or only a terminal. This type of production are only allowed in Chomsky normal form. So we will add new production rules to this CFG, that is A producing A and B producing B. And when we add this new production, we can directly change the small a to capital A, as we are mentioned in production rule, like this. But here it is no problem, because in production rule there is small a, small b can be. And also because there are 3, we only need 2. So we will add new production rule as R1 producing SA and R2 producing SB. This is the final. Next question is, obtain right linear grammar from the given finite automata. This is the finite automata. Directly writing the right linear grammar from this question is wrong. Instead of it, we have to first of all change the start symbol, the initial state to final state and final state to initial state, like we have done here. Final state is here and initial state is here, and we have to change the direction, like here from S to A, then A to S here, and this is here, but we have to write here, and here it is. Self loop will be as it is. So self loop as it is, directions changed, intermediate nodes, that is states are as it is and inputs as it is. Now from here we are writing production rule. S producing B, S producing B A. This is right linear grammar, so write this non-terminal in right side. In S get B, it is on it is. Okay. Now for today this is only there, guys. Thank you for watching. If you like this, if you understood this, then please like, share and subscribe. And if you have any doubts, then comment please. Thank you for watching. Peace out.